All right. Okay, let's start. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Ameya Jagtap, who is an assistant research professor of applied mathematics at Brown University. He received a PhD and master degrees both in aerospace engineering from the Indian Institute of Science. He then joined the Tata Institute of Fundamental Research Center for Applied Mathematics in India as a postdoctoral research fellow. Later, he moved to Brown University to pursue his postdoctoral research in the Division of Applied Mathematics. Due to his interdisciplinary background in mechanical aerospace engineering, applied mathematics, and computation, a key focus of his research work is to develop data and physics-driven scientific machine learning algorithms applicable to a wide range of problems in computational physics. His expertise lies in the field of scientific machine learning, deep learning, data-driven and physics-driven deep learning techniques with multi-fidelity data, uncertainty quantification, propagation, and the multi-scale and multi-physics simulations, and computational continuum mechanics, and spectral finite element methods, and we know DG schemes, domain decomposition techniques, etc., etc. He is also interested in the development of novel artificial neural network architecture, which give faster convergence. Today, Ameya will talk about scientific machine learning through the lens of physics-informed neural networks. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Ameya by asking one random question as usual. Today's random question is, where is your favorite place in the world?
I guess my hometown.
Your hometown? Somewhere in India, right?
Yes, yes, which I haven't visited since almost 4 years now. Yeah,
Oh,
so
no. Okay, so you missed that place, I guess. Okay. Stage is
yeah.
yours. Ameya.
Yeah. Sure. So thanks, Youngso, for the wonderful introduction. And today I'm going to present my recent work and some past work also. So the title of my talk is Scientific Machine Learning Through the Lens of PINNs. So I'm sure you must have already heard PINNs before, and maybe some of you are already working on it. So I know Young So is doing. So I saw his paper on Rome, PIN plus, for fast Rome methods. So with that, let's see an overview. Oops. Okay. Yeah. So first, we will quickly discuss the physics-informed neural network, or in short, PINN method. We will also see some performance improvement techniques, and we will see some of the scientific applications of PINNs where we can apply. I'll also discuss some domain decomposition based extensions of PIN, namely conservative PIN or cPINN, which is tailored towards conservation laws, and more general extended PINs or XPINNs, which is the generalized space-time domain decomposition version. And lastly, we will see the recent extension of PINs, which is a unified scalable framework for causal strategies with time domain decompositions. Okay. So traditional approaches like finite element method, finite difference method, etc., for scientific computation have undergone remarkable progress, but they still operate under very stringent condition. So basically, they require an underlying physical law, the precise knowledge of underlying physical law, also the boundary condition and initial conditions, and they often require time-consuming workflows such as mesh generation and the long-time simulation. So on the top of this limitation, the real simulation of real observation data for ill-posed inverse problem can be very costly. So basically here you are actually either discovering the missing physics, or you are calibrating the free parameters in the model. So I'm talking about in this region where we have some data available, and at the same time we also know the some physics. So basically it's an ill-posed inverse problems. So on the top of that, the data could be dirty, dinky, dynamic, and deceptive. Okay, so under these circumstances, the traditional method, they actually they suffer. Basically, it's not. Sometimes it's difficult or even impossible to solve such problem with the traditional method. So in this case, physics informed machine learning can actually help a lot, and it can actually use to solve these problems. So just a quick literature survey. So physics informed neural net machine learning is not new. It actually started proposed first by Lagares back in late 90s and early 2000. Okay, where he actually used neural network to solve PDE. Later on, OAD others propose physics informed machine learning for basically homogeneous problem. And then Cindy framework by Brunton for the dictionary learning of the dynamical system. And later physics guided neural network. At the same year, PINN also came, the first archive paper. Later, Wang also used physics informed machine learning for turbulence modeling, and the officially PIN was published in JCP in 2019. And there are so many methods similar to this, like physics constrained, physics encoded, physics guided, and so on. So in this talk, basically, we are going to focus on PINNs. So what is PINNs? So basically, it defines a paradigm that bridges the physical model with the observational data. So basically, we have this schematic representation of PINNs. So on the left-hand side, you have a typical feed-forward neural network whose inputs are the X and Y, which are the independent variables of the PDE. And the output is the dependent variable U, the field variable. So the field variable not only satisfies the data, the target data, but also satisfies the physics part, the PDE part, basically the governing equations using the automatic differentiation. So you can see the loss function, which consists of first term, which is the measurement loss. It's a data mismatch term. And the second term is the PD residual. Basically, we are trying to minimize the PD residual. So this way we can actually recast the original PD problem into an equivalent optimization problem. So minimization of this loss function will actually drive the solution. You will get the solution of the PD. Okay, so basically PIN aims to learn the surrogate U, theta tilde. Theta tilde is the parameters in the network, okay, for predicting the solution of the given PD. So by minimizing this loss functions, okay. So a PIN can use to solve both forward problem, and specifically it has an advantage of solving the ill-posed inverse problem. Okay, let's see one pedagogical example. So it's a simple viscous 1D viscous Berger equation. It's given here. And my initial condition is a simple sine wave, and my boundary conditions are 0. So these are the hyperparameter and parameter which I'm using. Data points are 150, which are randomly chosen. Residual points where we are evaluating the PD are 8,000. Activation function, hyperbolic tangent, learning rate, and so on. So okay, here is the pictorial representation. So this is the XT domains, computational domain, and you can see the data points 150 given by this blue cross. Okay, and here we compare the exact solution with the prediction, basically. And in this case, the L2 error after just 5,000 iteration is in the range of -2. So here we use simple Adam first order Adam optimizer followed by the second order LBFGS optimizer here. So this way we can solve the forward problems. So okay, before moving to some other application, let's discuss some of the performance improvement technique, which is the adaptive activation functions. So this is the very basic question, how to choose activation functions. And it is well known that there's no rule of thumb. It all depends on problem at hand, basically. So there are many open issues while training neural network, like vanishing and exploding gradients and the plateau phenomena. However, empirical observation actually shows that a well-chosen activation function can help gradient descent to not only converge fast, but also to generalize well. And some of the desired features of activation function is non-linearity, continuously differentiable, and the range. Well, of course, as I said, there is no rule of thumb for choosing the optimal activation function. So this actually the motivation to use the adaptive activation functions. So here we propose the adaptive activation function. It's a global adaptive activation function. So phi is my activation function, and calligraphic n, z is the input to the activation function, which is coming from the hidden layer. So instead of just this structure, we are actually introducing the additional parameter n and a, where n is the predefined positive scaling factor and a is my tunable parameter. So during initialization, we are initializing n is equal to 1, basically here, uh, so that we can always start with the actual fixed activation function. Okay, and once we start the optimization process, we are training a also, which is a tunable parameter, along with the other parameters of the network. So you can see that these are the different activation functions: sigmoid, tanh, ReLU, and leaky ReLU, and it actually gives different values for this a different structure with different a values. Okay, so this has already been implemented in the NVIDIA's modular software, previously known as SIMNet. We'll see some examples. We can also define, instead of a global parameter NA, we can actually define these parameters A locally, like layer wise. So for all K layer, also for neuron wise. Okay, so that actually also improves the performance of the neural network, as we will see later with some examples. Okay, so this is the theorem we proved. This is if you use the most basic form of the gradient descent optimization, and you satisfy at least one of the following condition, like constant learning rate, diminishing learning rate, and adaptive learning rate, then you can actually avoid the suboptimal critical points. So I'm not going to prove this, but you can see the proof here. It's very simple. It's a quite strong statement, but you can prove it for very basic optimization scheme, not for Adam, and we have not proved it for Adam and LBFGS, but for most basic gradient descent method. Okay, we also propose a generalized framework for adaptive activation functions. So it's Kronecker neural network. So instead of a single activation function phi, we have a series of activation function from phi 1 to phi k. And a particular case of this Kronecker neural network is the Rowdy activation functions, where in this case, my phi1 is any standard activation function. You choose anything like tanh or any ReLU or anything. And the remaining phi k equal to 2 to capital K are chosen. These are all sinusoidal, basically. So here it's like you are superimposing these sinusoidal noise on the top of the base activation function phi1. This is very helpful because it can actually overcome the spectral bias problem. Okay, let's see some examples. So a simple function approximation example is this one. Here we use the global adaptive activation function. So you can see on the left hand side it's a fixed, on the right hand side it's a global adaptive activation function, and you can see the prediction after 1000, 8000, and 22,000 iterations. So you can see that the fixed activation function actually stuck in the local minima even after 22,000 iteration. It cannot capture this simple function. But on the other hand, the global adaptive activation can easily capture it. You can see this loss function here. For global, it's green curve, dashed lines, and the fixed is the red curve. You can see that it's stuck in the global minima, but the globally adaptive activation function actually converges much faster. And you can see the variation of NA. We initialize NA with 1 initially, and now as the NA A value changes, you can see the loss function is also converging faster. And it actually it actually saturates at around 4.5 value. Let's see the another example. So this is now a PIN. We are solving 2D Helmholtz equation basically. Okay, it's a high frequency wave. You can see that this is the assumed form of the solution, and you can see that here blue curve is the fixed activation function, green curve is the locally adaptive activation function, and the red curve is the Rowdy function, which we discuss at the end. And among all, Rowdy performs best. So Rowdy net 5 means we use k is equal to 5 terms. Of course, Rowdy is expensive because we are adding multiple activation function, but then there are different ways to reduce the cost, like transfer learning, which already discussed in the original paper. You can also see the relative error on the right hand side. In this case, Rowdy is actually converging much faster compared to fixed and the locally adaptive activation functions. So recently we also put this survey paper, which was accepted in JML MC journal, where we compare we discuss more than 180 activation functions and compare using this TensorFlow, PyTorch, and JAX. We also compare both fixed, adaptive, and other types of activation function. So let's see some scientific applications here. So first one is high-speed flow. So that's basically my PhD topic. I worked on algorithm development for high-speed compressible flows. So here, in this case, this is basically a semi-inverse problem. The aim is to solve infer the equation of state, basically the gas constant gamma, using only Schlieren data, as well as the pressure data and inlet conditions. So you can see this XY domain here. So this is a steady state problem. So we have an oblique shock wave, which is actually coming from the left bottom corner. Okay, and it is an inclined shock wave. So there are two cases. In first case, we just chose the training data point randomly, which is the left hand side case. And on the right hand side, I chose training data, which is actually where I'm coalescing more points along the shock. Okay, in this case, since it's an inverse problem, from the Schlieren data, I know where is the high gradient available, and I can actually take more points in that region. And you can see the results in the table below. So the true value of gamma is 1.4, that's for air. And this is the gamma with clean data, there is no noise. The random value, converged value, and the clustered value. So cluster value is obviously, it's much accurate than random, because a slight change in the orientation of the shock can actually give you completely different gamma value with fixed initial conditions. And with increase in noise, you can also see with 1% and 2% noise, I'm getting the clustered data points giving much better results compared to the randomly chosen points. Here is another example where we are actually quantifying the material properties. In particular, we are actually quantifying the polycrystalline nickel material. In this case, we have only the displacement data, and the aim is to infer the compliance coefficients of the material. So in this case, we have the X1 displacement data, which is available from the experiments, and X2 displacement data, and X1 and X3 displacement data we actually got it from the FEM solver. So here is the comparison of the displacement data actual versus PIN on these 4 locations. You can see that they are actually matching pretty well in this case. And for single crystal nickel, the speed of second shear wave is actually 2.97 millimeter per microsecond. And these are the plots which actually shows the space dependent second shear wave, the left hand side plot, which is actually we are plotting on x1 x3 plane. And you can see that the range is from 2.95 to 3. Which actually confirms the presence of the polycrystalline nickel material. So although we couldn't capture the crystal boundary clearly, but we actually at least confirmed that it's a polycrystalline nickel material. And on the right hand side, it's a C44 spatial variation. So this way actually PIN can be also helpful in quantifying the material. One more example where we solve the inverse water wave problem. Basically, in this case, the aim is to infer the velocity field and the corresponding forces on the wall using only water column height. So the governing equations are Serre-Green-Nagade equations, basically. And this is the first case. So you can see that this is again an X and T plane, 1D example. And eta is my water column height. And you can see these, I'm not sure it's very small, but these are the black dot lines. You can see that these are 12 gauges which we placed along the x-axis, and it gives a time series data. So that's the only data we have. In this case, 12 gauges. On the right hand side, we have 20 gauges. And you can see the predicted velocity at the bottom for 12 gauges and 20 gauges respectively. And that's the pointwise error. We are plotting pointwise error in the water column height also because we don't have all the information of the eta. We are just using some finite set of values here. Second example in this case is the solitary wave reflection. So you can see the wave which is actually hitting this column and then passing. So we use the low fidelity gauges given by the black dots and the high fidelity gauges. So low fidelity around 1200 and high fidelity 50 points. And then we use multi-fidelity pins. So basically the aim here is to map the low fidelity data on high fidelity gauges, basically, and then use those high fidelity data, feed those high fidelity data to the PIN network for the training. So that's basically the correlation between reference and the predicted high fidelity data, low and high fidelity data. And that's the we also computed, along with the velocity, we also computed forces which are acting on the wall. So okay, you can see there's this is the wall, small rectangular portion. I just take upper half portion here. So the left hand side is wall 1, the top one is wall 2, and the bottom one, the right hand side is the wall 3. And you can see the forces on these 3 walls, the reference solution and the multi-fidelity pin solution, and they're matching pretty well. So that's the pointwise error. Okay, so let's discuss some of the limitations of pins. So the first one is due to high dimensional non-convex optimization problem, the accuracy of the method suffers. So it actually, the best accuracy what we get is around -4, -5. Or now with JAX, it is better than that. I mean, I can even get -5 plus accuracy, but it's not comparable with the spectral accuracy. And the second limitation is the large training time, because specifically for the forward problem, because PIN is not yet it is not competent with the traditional numerical method when the forward problem is the concern. So aim is to tackle the large training time here. So let's see some of the classical approaches. So first one is the data parallel approach. So here we have the data. We are actually splitting the data into a number of chunks, which is exactly equal to the number of processor, and we initiate same neural network, okay, with these data set, and then we use distributed optimizer, which average out the gradient loss on all route processor through all reduce operation, and then we average gradient of the loss function, okay, and to update the weights of the network. So that's one way, data parallel. Another one is model parallel approach. So here we are splitting the data into small batches, okay, and during forward pass, well, in this case, all the hidden layer L1, L2 actually are distributed to the processor. So now we have different processor for different layer. Again, my neural network is same. So during forward pass, as layer 1 L1 process batch 1 B1, okay, it actually passes it to L2, and then it start processing B2, and that's how they actually finishes the forward pass. And once L4 finishes working on B4, the backward pass kicks off, and it finishes the epoch with the pipeline approach, and then they update the parameters of the network. So in both cases, you can see that there is a single neural network is used. So our approach is basically a domain decomposition based approach. Uh, it's very simple. So we have a domain. You just divide that domain into a number of subdomain, and instead of single pin, you deploy different pins in each subdomain. And then you need an additional interface condition along with the PDEs to stitch these subdomains together. And additionally, you also get the interface loss function, loss term along with the data mismatch and the PDE residue term. Okay. So what's the advantage? Of course, it has parallelization capacity. And then, okay, so this is also there for data and the model parallel approach. That's why actually I just put it in the red color. And these points in blue color, these are the additional advantage of domain decomposition based pins, which are not there with the model and data parallel approach. So it has a local representation capacity. We can actually deploy a locally powerful neural network. If we are solving an inverse problem, and you know that some idea, you have some prior knowledge about the complexity of the solution. Second, you can efficiently adjust all the hyperparameters of the network using meta learning approaches. And third, we have also seen the reduction in the error propagation in the domain, basically because we are supplying additional interface condition inside the domain. Okay, so first domain decomposition method is conservative pin or cPINN. So basically, in this case, the interface conditions, first one is the flux continuity condition. So it's similar to finite volume method. We are actually where we are enforcing the flux continuity condition in the normal direction. That's why that's dot n is there. And second condition is the average solution continuity condition. That's the U average. So here is the idea. So if you have a solution which is smooth, so the average value given by the two networks. So in this case, you have subdomain 1, pin network 1, and on the other side, you have subdomain 2, pin 2, and this is the interface. So when the solution is smooth, the average value the average continuity condition boils down to solution continuity condition. So that's the average point here. But when the solution is discontinuous on the interface, which is a possibility when you are solving a hyperbolic conservation laws, which admit discontinuous solution, then actually we are enforcing this value at the interface. That means we are actually capturing these shock waves with single point, basically, at least theoretically. Okay, let's see some examples. So this is a simple viscous budget that we have seen earlier. So here we are decomposing the domain into 4 parts. So you can see along x-axis, these 3 white lines. So domain 1, 2, 3, and 4 from top to bottom. And these are the parameters we used in the subdomains. And actually that's the point-wise error shows. And we also just plotted the relative L2 error without average term. That means just enforcing the flux continuity condition, and with average term along with the flux continuity condition. So you can see that with average term, the red curve, the relative L2 error decreases much faster compared to the without average continuity condition term. Excuse me. Okay, let's see one more example. It's a lead driven cavity incompressible Navier-Stokes example. Basically, we have 12 subdomains here. Sorry. we have 12 subdomains here, and these are the hyperparameters of the each network deployed in these subdomains. That's the comparison of the velocity field u and v with the GIA GIA data. I mean data given by GIA, and they are actually matching pretty well. So we will use this example for parallelization later on. Let's see some inverse example, inverse viscous Burgess. Again, it's a Burgess equation. I'm just giving you simple example just to show that how easily we can apply. Okay, in this case, we have a data given, I mean, obtained by from the viscous Burgess equation, and instead of we are actually using, instead of using the exact equation with the parameters, unknown parameters, we are actually supplying additional terms, and our aim is to find out these parameters beta, nu, and alpha. So basically we have unsteady term, nonlinear convection, linear convection, viscous term, and the third order term, dispersive term basically. And with viscous Burgess equation, we know that my beta should be 0 because the flow is from basically left to right. My nu should have some value, a positive value, because it's viscous equation, and my alpha should be 0. Okay, so because it's not dispersive. So we initialize these, again the same problem, what we consider the forward problem last time with 4 subdomain. We initialize alpha, beta, and nu differently in these subdomains, and you can see that once the optimization procedure starts, they are actually going towards the exact value. Okay, so you can, it's interestingly you can see that new value, it actually overshoots the exact solution, because alpha and beta, they were still converging. The moment they converge to their original exact value, which are 0, it actually started then converging towards its original value. So these are the comparison, cPINN comparison, which are pretty accurate. Okay, so what next? So basically, it would be really advantage if we use the domain decomposition strategy for every PD and not necessarily for conservation law. Moreover, if you have domain decomposition in space and time, that would be really helpful for many large scale problem. So yes, we can do it. The answer is XPINN here. We can actually employ this. So let's see the interface condition. So the first interface condition is same as cPINN. It's average solution continuity condition. And the second interface condition is the residual continuity condition. So basically, we are saying that my residues are same along the interface. So this actually will help you to decompose the domain in space and time arbitrarily. So we don't have to worry about the shape, and even if it is a moving domain, it will be really helpful. So because there is just like a flux continuity condition, we are not finding any normals here or nothing. So it's just a residual continuity condition. And plus you can add additional continuity condition if you have any, like integral constraint, higher order derivative requirements, and so on. So advantage over cPINN, we can extend it to any differential equation. As I said, we can actually decompose in space and time. And implementation wise, the interface conditions are simple because we don't have to find out normal direction, which would be really complicated in terms of moving interface in high dimensional problems. Okay, here is the comparison of PIN, cPIN, and XPIN. Spatial domain, yes, cPIN can do, XPIN can do. Both cPIN, XPIN has parallelization capacity, local representation capacity, and efficiently adjust all the hyperparameter. cPIN can be actually applicable for only conservation laws, but XPIN can be used for any differential equation. Interface conditions are complex in cPIN, but it's simple in XPIN. Moreover, XPIN has additional spatial temporal domain decomposition capability. So let's see again, same viscous Berger, and now we are decomposing domain into a dolphin shape, domain 2, and the outside blue C is the domain 1 basically. And you can see the hyperparameters here. And this is the predicted solution versus exact solution. And the relative L2 error after 15,000 iteration is this much. So the whole point is to show that we can actually decompose in such a weird way in space and time, and we can easily solve this kind of problems with XPINN. One more example, 2D compressible Euler equations. So we have a oblique shock reflection test case. The shock actually created at the top left corner, it actually then hits the bottom wall and reflected back. So in this case, you can see a peanut shaped domain, domain 1 and outside domain 2. So I chose this because eventually the shock will hit it will pass through these two subdomains and reflect it. And here is the prediction, pressure, density, and velocity in x and y direction. And this is the comparison with the exact solution at location y is equal to 0.5. So this is pretty much accurate results. We can see the smearing of the shock. But of course, if we use more points or active learning strategy or something like that, then we can actually get much better results. We have also implemented a cPINN XPINN parallelly. So I'll just quickly show you some of the results. Okay, this is the computation versus communication time on GPUs. So basically, that's the right-hand side plot is for the cPINN. For the cPINN, you can see that computation time in pink color and the blue color, and the communication time in pink. In XPINN on the right hand side, the communication time is more. That's obvious because we are enforcing the residual continuity condition. We are actually enforcing the whole PDE to be continuous along the interface condition, which needs more communication compared to just enforcing the flux continuity condition in cPINN. This is the weak scaling we have done, and these are the sample per second plots on number of GPUs. We use till 24 GPUs. This is for XPINN and this is for cPINN. Obviously, for XPINN, sample per second is less compared to cPINN because of obvious reason, but it matches well with the theoretical curve. And that's the strong scaling basically. So that's the speed up and the efficiency. You can see that for cPINN it's almost linear, slightly less, and for XPINN it is again lesser than cPINN speed up, because again the communication and computation time is more for XPINN compared to cPINN. In terms of efficiency, cPINN almost hit 80%. And XPINN hits 70% basically. If you have any question, you can ask me. You don't have to wait till end.
Anyone wants to ask question by unmuting yourself? I know Joseph has putting the questions in the chat.
Okay. Maybe I can.
Joseph, do you? Yeah, Joseph, do you wanna?
Yes, I have a question.
Yes.
Because now you have the composition of the domain, but in case you have, for example, a shape that is discontinuous from your other domains, is it possible to do XPINNs in that case?
What do you mean by decompose?
Like if you have like cylinder or something like, and you want to do aerodynamics or fluid.
So yes, you can still do it, right? So the domain is still it's a single domain, right? So it's not simplex. It's you mean to say domain with some voids or holes?
Yes.
Yeah, you can still use these domain decomposition based methods.
Thank you.
Thank you very much. Very interesting presentation. The domain decomposition, is that a manual process or is there a way to automate it based on the geometry characteristics of whatever you're analyzing?
Yes. So I'll show you in my some future slides. You can automate that process. We just published that paper in SIAM. Based on the based on some bounds. So, but of course, it's not that easy, because if it is an inverse problem, then of course it's easy. You can automate this process, or we are also working on some moving domains, basically where the interfaces are moving. Because with time the complexity can move in certain parts of the region. So in order to track that complexity, we need the moving interface, subdomains. So in that case, also you can also do that. But we are still working on those ideas.
Thank you.
Okay, Amir, you can go on.
Okay. So this is the part we recently worked on, where we propose a unified scalable framework for causal sweeping strategy for pins, and with their temporal decomposition, domain decomposition. So some of the limitations of vanilla pin, we can see here, figure A, figure B, and figure C. Figure A is the simple linear convection equation. Figure B is again the same equation, but for short time, 0 to 1. And figure C is the Allen-Kahn equation. So we have seen some of the issues with vanilla pin. Some of the limitations is zero solution propagation, specifically for the boundary condition, case A. So you can see that the boundary is periodic. It satisfies the initial condition, and it also satisfies the periodic boundary condition. Even though the solution is zero, it still satisfies the boundary condition, right? So that's one of the issue we have seen. Later, we also have seen no information propagation at all. So you can see that in this case, this is the exact solution. In this case, this is the exact solution, and this is the exact solution, and these three are predicted solution. So the predicted solution, there is no information is propagating at all. And the third one, this is the predicted solution, and you can see that this is basically an incorrect information propagation. So it converges, but actual solution is different from what you are getting. Okay, so some of the strategies that has been proposed to overcome these limitations are time domain decomposition strategies. So here I'll show you the pictorial representation, A, B, C, and D. So A is the adaptive time sampling. So basically it actually has, you're splitting the domain along time axis, okay? And you have single network. So once you train the network subdomain, you just add another subdomain and so on till you finishes the last subdomain. Okay, so that's the adaptive time sampling strategy. Second one is BCPIN. So basically it's a backward compatibility spin. So once you train the network, you can see this red points here. Once you train the network, you convert that predicted solution into a data point. So that will be a data point for the ongoing ongoing training in this network, shown by the black lines. Okay, so that's how you actually march in time. And then there are time marching techniques and the XPINN, which we have already discussed. So in this case, time marching is again time splitting, and they use separate networks instead of same network. Okay, that's the difference, and we already seen XPINNs before. So these strategies can actually help in tackling all these issues which we discussed previously. Moreover, it can also tackle the long time integration issue. On the other hand, we also have causal weights. Okay, so basically in this case, we have single network, and we are defining a collocation point mask that moves in time inverse exponentially proportional to the magnitude of the prior. So I'll come to that in more detail. So here I'm trying to classify the causality enforcement method into a hard causality, soft causality, combination of both, and non-causal. With time slab scales. So basically these are the discrete enforcements on the scale of the partition slab, and the sampling rate. So here it is the continuous enforcement on the scale of the collocations point sampling. You can see that these methods are actually finding some space here. So like adaptive time sampling is a soft causality plus time domain decomposition, time matching, BCPINNs, and XPINNs. They're all time domain decomposition methods. And causal weights is not time domain decomposition because it actually put more weights for the whole domain, but it can be do for time domain decomposition too. So you can see here there are some missing methods here. We'll try to fill this gap. Okay, so idea is the first idea is the stack decomposition. So this actually bridges the sequentially trained time marching methods and parallelly trained XPIN. So in this case, we are training one subdomain at a time. So it is shown by the yellow box, the yellow color. And these are the finished, already finished trainings zone. And here it will be a future training zone. In XPIN, we are training everything at once. Okay, so stack decomposition is in between these two. So instead of just single domain, we can actually choose number of more than one subdomains to train. So that will actually reduce the training cost. Okay. Second idea is window sweeping. So basically it's a generalization of time sweeping collocation point methods like adaptive and the causal weight. So you can see that the point weight along y-axis and the time on x-axis. So you have a hard causal points where you are applying a boundary condition or initial condition at the starting. Okay, here weights are more, and then it is actually gradually decreasing. Okay, so we can play with how to decrease these causal weights, and for future set our weights are very low. Okay, so one example here, it basically actually introduces a kernel, variable kernel, like uniform, linear, or error function. So this is the example of error function here. So how these error functions, the weights are moving in time. So you can see that this is the blue line with boundary condition weight. These are hard causal. The green with the null set, the weights are very small or zero. And then the gradual increment in the weight. So we are putting more weights to learn the solution for small time. And then we are slowly increasing that. It actually sweeping that weights in forwarding time, basically. Okay. Keeping this hard causal boundary conditions and null state for future points can reduce the computational cost drastically. Okay, so we can actually put these. Now we can see that we can actually try we are able to fill these gaps with stack domain decomposition. We can actually enforce both soft and hard causality in time domain decomposition, and also in sampling scale we can also employ both in a hard and soft way. Okay, the unified framework is to use both stack decomposition as well as window sweeping method together. Okay, on the top of that we also use transfer learning and fine tuning. So basically once we train one subdomain, we can actually use the same weights and the train weights and bytes as an initialization for the next neural network for the future subdomain. Okay. Okay, so algorithm is very simple. So we just need to choose the stack decomposition parameters here, like number of divisions n in time, ds, how much weight, how many subdomains you need to train at once. Okay, and so on. And then choose interface condition, whatever the condition you have, residual continuity or any other continuity condition like initial condition or higher order initial condition if you are solving higher order PDEs. And then of course the time transfer learning parameters, you can choose how many numbers you want to keep fixed and how many layers you want to tune it further. And then we choose window sweeping parameter like BC set, null set, weighting kernel, and kernel hyperparameters. And finally we run the model. Okay, so let's see the simple Cote de Vries KDV case. It's a third order dispersive model. Okay, so initial condition is simple cos function with and the boundary condition is periodic. So here there are two cases. It's short time interval 0 to 1 and the long time integration 0 to 5. So for short time you can see that PIN error it is almost in the same order with the SD. SD stands for stack decomposition and WS stands for window sweeping schemes. So we applied it separately and together. So they are more or less same. But when you go for large, long time integration, okay, so you can see that the combination of SD and window sweeping gives much better results, and also in terms of computational cost, it is very cheap compared to the original vanilla PIN method. So as I said, it can actually solve the long time integration problem easily without any issues that we discussed before. Okay, this is the thing we recently published. That's what I said. So the first one is when do XPIN improve in generalization? This is the SIAM paper. Here we discuss how to decompose the domain and how to automate the process to decompose the domain. And we also published this first comprehensive theoretical analysis of PIN XPIN for nonlinear PDE, basically for Navier-Stokes equation. That's the error estimates we propose. The idea is very simple. You can actually give the actual error in the solution in terms of the training error. So today I'll not discuss these two methods, but hopefully in future sometime I'll discuss. So here is the conclusion. So first we presented PINNs. We have also seen some application of PINNs, high-speed flows, material quantification. We have seen performance improvement technique like adaptive activation functions. We also discussed some domain decomposition based strategies like cPINN and XPINN, which has obvious advantage over vanilla PIN like parallelization capacity, local representation capacity. Also, it's computationally very efficient for problems like high dimensional problem or big data basically. And we also discussed a recent work on unified scalable framework for causal strategies with time domain decomposition that basically overcome many limitations of PIN, including long time integration. So here I'll stop and I'll happy to answer your questions if you have any.
Thank you. Thank you so much for the wonderful talk, Amiya. Let's have a Q&A session. So it's open to anyone. Well, I know, Joseph, you have asked during the talk, but I know you have more questions in the chat. Do you want to unmute yourself and ask those questions, or it's up to you? Joseph, are you there? Is he here?
Yes, sorry, no question. Thank you. Thank you for
no question. All right, sounds good. Okay, anyone? Either unmute or raise your hand. Well, while you're thinking about it, okay, so if you go to very beginning, you're talking about the Cindy as a the physics informed method. In my understanding, Cindy is not physics informed method. It's a physics discovery method. It's not.
Yes. So basically, they provide the dictionary learning for dynamical system.
And those dictionaries are provided by the user. It's not driven by physics.
Okay.
Yeah. So it's I just wanted to point out that. All right. And in the conclusions, you are claiming that it's very efficient for the high dimensional problems. What do you exactly mean by high dimensional? Like high dimensional in 3D, like the 2D, or like parameter space being high dimensional?
Basically, I'm talking about physical dimension, 3-dimensional. now we are actually working on a turbulence problem.
Mm-hmm.
It's 3D turbulence, so we have DNS data, and it's a long time integration. So we decompose that problem using XPINNs, and it can actually, the aim is to infer the the material or the fluid flow properties, basically the stress strain relation for that flow. Basically it's turbulence model, and there is no way you can fit that huge amount of DNS data in a single pin network. Okay, so maybe soon, in a couple of weeks, we'll put that paper on archive where we have used XPINNs, and the results are much promising. So it can actually solve this kind of physical high dimensional problem. Basically it's 4-dimensional including time, and that's what I mentioned. That's what I meant by.
Okay.
But of course, as far as parametric space is concerned, high dimensional parametric space, that's also a good idea to decompose that space, and if some strategy can be developed to decompose that kind of high dimensional space. Yeah.
Got it. I'm looking forward to that paper you're gonna share soon on the 3D-dimensional, the Navier-Stokes,
Yeah.
the turbulence problem, DNS. So you use the data there.
Yes.
You are not only relying on the residual terms.
No, of course, we have the physics informed part, but we are also enforcing the DNS data. We are enforcing the equations, and aim is to infer all the turbulence parameter in the model, turbulence model, basically.
Yeah. Okay. Sounds good. One more question. When you say it's improved from previous, the method, it's with respect to the previous pins, I assume, not with the comparison with the traditional numerical method of solving those PDE.
Yes, the last approach, you mean to say?
Yeah, for example,
yes.
one you were mentioning, like the DNS 3D, it's improved.
Well, this is an inverse problem. Basically, the DNS turbulence problem you are talking about.
Inverse problem. Okay.
Yes. So I am actually comparing with the vanilla pin, basically, not with the traditional method.
I see. Okay. Thank you. Jolton, you have a question? You can unmute.
Yeah, thanks, Amir. Very nice presentation. I have to admit, I don't know a lot of details on the pins, so this question might be a little silly. But in the beginning, you mentioned that the advantage of pins is that you can deal with, dirty, noisy data and all of those things. And so I wonder and I know you didn't cover this, but I wonder your thoughts on like how bad can it get in terms of noisy data or missing data or just faulty data when pins can recover the structure underneath. So do you have any pointers?
In this talk I have not covered, but there are other versions of pins like multi-fidelity pin, which can actually tackle low fidelity data. And in that paper from our group, we have shown that it can actually tackle from say 1% to around 5% noise in the data. We assume the Gaussian noise. And another framework is the Bayesian pin framework. There actually then there are other ways to quantify the uncertainty related to the solution with this noisy data set. So yeah, pin can definitely tackle a noisy data set, and we have in the original paper of pins in Mazia's paper, he has also shown some inverse problem where they are adding some noise data around 5% noise, and then they try to recover the original equations or parameters in the model. So yeah, it can still tackle. I mean, of course, for large data, it's a challenge for PIN too. But till 5%, it's fine.
Cool. Thank you.
Sounds good. Okay. Any other questions, guys? Well, if not, let's thank our speaker for the wonderful talk and the Q&A sessions.
Thank you, Youngso, for the
Oh.
invitation.
Actually, Sungwan, you raised the hands. Why don't you unmute yourself? And
Hi, thank you for the talk. It was interesting, and
Hello.
I guess I'm also not expert in the PIN, so I might like not fully follow your talk, but I guess my question is like I think you mentioned like when you're getting into like turbulence, you cannot just use the single neural network, and so
Yep.
I guess based on your experience, like, do you have some sort of an idea, like how many set of neural network do you need?
Okay. In this particular problem that we are solving, we had around 1024 snapshots, 3D snapshots of the turbulence problem, and we use different scenarios. So, for example, we use different GPUs, around 64 GPU, 128 GPU, and even 1024 GPUs. And we have shown in this paper that how it scales. Of course, with 1024 GPUs, the results are much better because you have 1024 networks basically in this case. With increase in number of networks, so you have more expressibility. The approximation will be much better as the expression power for the neural network increases. So that's what we have shown. So hopefully we'll put that paper soon on archive.
I see. Yeah, thank you so much.
Welcome.
thank you. Is there any other question? Last chance. All right, let's thank our speaker. Thank you so much, Amia, for the wonderful talk.
Thank you.
And as I said before, hopefully after this talk, someone is going to contact you and then.
Yeah.
Right.
Hope so. Yeah. Thank you, Youngso.
All right, sounds good. Thank you, everyone.